Okay, welcome to example number 8. We have a circuit containing 4 resistors that are in series with one another. You'll notice that they're basically aligned end to end as we go through here. And this is called a series connection. There are no junctions in this entire loop. So what we have is that the current should be the same that enters the first resistor as it is through the last resistor. And each of these middle resistors also have the same current. And that's equal to the total current through the circuit. So let's start off by finding the current through each resistor. Now, to find the total current, or the current through each resistor, we have to start by finding that total current. And in order to do that, you need to find the equivalent resistance of the circuit. So essentially, we need to find the total resistance of these 4 resistors. So to start off part A, we'll write the equivalent resistance is equal to R1 plus R2 plus R3 plus R4, and then you'll simply add up those 3 resistances. You have 3 ohms plus 1 ohm plus 2 ohms plus 10 ohms, which gives you 16 ohms. Okay, once you know the equivalent resistance, then you're essentially replacing these 4 resistors with one single resistance. And that single resistance would have a voltage drop that is the same as the battery. So the EMF is equal to the current that leaves the battery and happens to go through resistor 1, resistor 2, resistor 3, and resistor 4, and then comes back into the battery. So that multiplied by the equivalent resistance gives you the total voltage. The total voltage is 80 volts time equals I times the equivalent resistance of 60 ohms, which gives you a current of 5 amps. And then once you know that current of 5 amps to the battery, remember that total current is also the current through each individual resistor. So current through number 1 resistor, and through number 2 resistor, and number 3 resistor, and number 4 resistor is going to be the same as the total current, which is 5 amps. Moving on to part B, well, we've actually solved that. Part B is right here. And then so we're actually ready to proceed here now to the potential drop, or the voltage across the first resistor. So let's say A to X, and then we'll do the next one from X to Y, and then say the next one Y to Z, and then the last potential drop from Z to B. So the voltage drop across the first resistor, which is A to X, is basically that current that goes through it, so I, or I1, multiplied by its resistance. So we would get 5 amps multiplied by 3 ohms, which gives you 15 volts. And you can do a similar thing for voltage 2 and so forth. So let me go ahead and write that in. And so here I have written 5 volts, 10 volts, and 50 volts. And if you look at this, the sum of these voltages, 15 volts plus 5 volts plus 10 volts plus 50 volts, will add up to a total voltage of 80 volts. And that should be a good check that that EMF is really equal to the sum of the voltages of resistors in series. Okay, moving on to part D, which is finding the power dissipated by each resistor. Okay, now you can calculate the power many ways. You could use power equals current times voltage, since you know each current and you know each voltage. You could also use I squared times R. Once again, you know each resistance and current, or you could also use V squared over R. Just one thing that I find that is good to know conceptually is that since all these resistors all have the same current, and if you were to compare these and find out which was the brighter bulb, because we know that the brightness is related to the power, then what you could use is I would prefer when we do series circuits to use P equals I squared times R, because they all have the same current. Therefore, the circuit with the resistor with the greater resistance is going to have the greater power, so because P is proportional to R. So if I want to find power 1, I would simply take that current of 5 amps squared and then multiply by the resistance of 3 ohms, and that gets me 75 watts. And then I can go ahead and do a similar thing for all the other 3 light bulbs. And so you can see that I've done correspondingly these other powers. And once again, you notice that the the resistor with the greater resistance has the greatest power, 250 watts. Last part, part E, we want to find the total power. Total power can again be calculated in many ways. You could use I times V, or I squared times R, or V squared over R. Any of those methods would be fine. You could use I squared times R, but again, you're using the equivalent resistance because you're looking for the total power of the circuit. So assume that all 4 resistors have been made into one resistor, which would have a resistance of 16 ohms. So one could use 5 amps squared multiplied by 16 ohms, and that gets you 400 watts. Alternatively, you could even just look at these 4 powers and say the total power is really power 1 plus power 2 plus power 3 plus power 4, and simply add them up. 75 watts plus 25 watts plus 50 watts and plus 250 watts, and that will give you 400 watts.